तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Good morning. So, last time we had introduced Coulomb's law, and I had also started talking about something called the electric field. I want to continue on that, and I will repeat a little part of the last class so that you feel comfortable with the material. So, we had Coulomb's law, and Coulomb's law said force on a charge Q2 due to a charge Q1, you draw a line through Q1 and Q2. The force is along the line joining Q1 and Q2, pointing away from Q1, and it is equal to Q1 Q2 over 4 pi epsilon naught times 1 over R12 squared in this direction, which your textbook calls A12. So, this was what Coulomb found, and we worked out some examples of what happens when you use it. Now, this force is a force exerted on a particle. If you ask what this force depends on, force depends on Q1, depends on Q2, it depends on the location of Q1, and it depends on location of Q2. Given these quantities, you get a number, you get a vector. Now, it has been found to be very useful if instead of talking about force, we talk about force per Coulomb. You can see that the force is proportional to Q2. So, if we replaced Q2 by twice Q2, the force will be twice. If we replaced it by 4 times, the force will be 4 times. So, we could talk about a force per unit Coulomb, and then all we have to do is multiply by Q2 to get the actual force. This force per Coulomb is called the electric field. It has got a symbol E. The units of force are newtons. So, the units of electric field ought to be newtons per Coulomb. We actually give it a different unit, but this is correct. There is nothing wrong with this unit, but when we invent electrostatic potential, we use that instead to give a unit for the electric field. It is defined as Q1 over 4 pi epsilon 0, 1 over R12 squared A12. Q2 is missing. So, E is actually equal to the force F divided by Q2, because you can see that is the difference between this formula and this formula. Now, this seems rather arbitrary. I mean, I could have divided by Q1 as well and got some other vector which I then say is per coulomb per coulomb. If I have got the force, why do I need to complicate life and create a new vector? Well, there is a reason. It has to do with how we view Coulomb's law. Now, if you look at a charge Q1 and you look at another charge Q2, we are saying that there is a force on Q2. Now, how is it that Q1 created a force on Q2? In the old days, during Newton's time, it was thought that everything acted at a distance. That is, the sun pulled the earth from some 160 million kilometers. The same way, you could think of protons and electrons interacting over a distance. But there is another way of looking at things. You could say that the presence of this charge has polarized this material that's around this charge. That is, the material in the presence of this charge has actually got stressed a little bit. Because of that stress, any time you place a charge there, that charge receives a kick, and that kick is what we call the force. This picture is only a picture. I mean, one could in fact do all of electromagnetic theory without actually requiring this picture. You could work with Coulomb's law and equivalent laws that work at a distance. But modern physics has shown that there is a lot of validity to this picture of stress vectors, stress fields. For example, all of special relativity and general relativity requires such a picture. All of quantum mechanics requires it. All of particle physics requires it. So, today's scientists are pretty much convinced that the picture of particles which create stresses in the space around them called fields, and these fields in turn react on other particles causing force. That is the picture that is correct. And if that picture is correct, then rather than talking about fields, we can talk about, rather than talking about forces, we can talk about fields. We can ask, how is this stress created? So, that is this equation, which is the electric field is equal to the originating charge divided by your normalization constant 4 pi epsilon naught 0 times, at this point there is some distance, call it d, 1 over d squared along the direction d. Now, there is a difference between this formula I have written down and the previous formula I wrote down here. In this formula, I was still talking about the electric field as evaluated where Q2 is. So, this was just a shorthand for Coulomb's law. But when you come to this equation, there is no charge here. The only charge is sitting here. However, I am saying that there is a potential force, a force waiting to happen at every point in space. All of space has got unhappy, all of space is stressed out because this charge is there. And the moment you put any other charge there, it reacts violently and gives it a kick, and that is Coulomb's law. So, now this electric field is a function of this vector d, this vector connecting the location of charge q1 to any point in space. So, if you wanted to know the field there, this vector would be d. If you wanted to know the field here, this vector would be d. So, this is now a definition of a vector quantity which is a function of a variable, independent variable. Okay. The independent variable itself happens to be a vector. We are used to seeing functions f of x. For example, f of x equals sin x. So, there x is a real number, f of x is another real number. So, if x was equal to 1, f of x was equal to sin of 1, and if x is a variable, f became a function. Similarly, here I have a vector variable, that is d is actually d along x in the x direction plus d along y in the y direction plus d along z in the z direction. So, this is my variable. Instead of one dimensional, it is three dimensional, and this vector function is a vector function of these three numbers dx, dy and dz. So, it is a more complicated beast than your simple function like sin x, but the equation it satisfies is a very simple equation. It is nothing but Coulomb's law, except it is Coulomb's law applied to where there is no second charge. It is applied to any arbitrary point. Now, last time we talked about the superposition principle. And what that said was that the force at any point due to a bunch of charges, so you had a collection of charges and you put a charge, well, let me call it small q. So, these were q1, q2 etc. up to qn. Then I said superposition told us that the force on this charge small q was equal to small q over 4 pi epsilon naught sum I equals 1 to capital N q sub I divided by this distance, which I called Ri. So, Ri is nothing but the distance vector between the charge qi and small q. So, this was Coulomb's law generalized for n points. Similarly, now you can divide through by small q and you get the electric field at any point r. So, I am choosing some point r. Let me draw a coordinate system now. This is x, this is y, this is z. So, this vector from the origin is r. This vector to my qi is, well, I will call it rho I. This is not standard notation, but it does not matter. So, the charges are q1, q2, q3 up to qn, all at distances from the origin given by vectors q rho I, rho 1, rho 2, rho I, rho n. I want to know the electric field at this point. There is no charge there anymore. So, how would I get it? My answer is I will put a charge of 1 coulomb, measure the force. Electric field is the force per coulomb, which means it is the force on 1 coulomb. What do I get? I get it's equal to 1 over 4 pi epsilon 0 sum I equals 1 to n q sub I, but I now need this distance, this vector. Now, if you look at this vector is really the vector r minus the vector rho I. That is because if I call this vector s, then I have that rho I plus s is equal to r, because I have take this vector rho I, at its nose I place the tail of the vector s, it reaches the nose of vector r. So, this must be true. If I take s to the other side, sorry, if I take rho I to the other side, then I get s is equal to r minus rho I. So, I know my distance vector. I am going to say it is equal to s I squared unit vector along S I. But if I keep inventing symbols, it does not really help us. So, I instead go back to what S I is. So, it is equal to 1 over 4 pi epsilon naught sum I equals 1 to n q I. When I say S I squared, I really mean take the magnitude of the vector S I and take its square. So, magnitude of r minus rho I squared, and this unit vector is nothing but r minus rho I unit vector along that. What have we gained? What we have gained is, if I have a collection of charges and I am given that collection, so the charges are fixed in location. I now have a quantity which is a function of one independent vector variable, which gives me the potential field at any point given all these charges. It is still only Coulomb's law, because all I have to do is multiply by q on both sides and I get back force due to charges according to Coulomb's law. Now, there is one important simplification you can make to this. Supposing I multiply and divide by magnitude of r minus rho I, what do I get? 1 over 4 pi epsilon naught sum I equals 1 to capital N q I divided by r minus rho I cubed. Now, out here if I multiply by magnitude, a unit vector times the magnitude is the vector itself. If I have any vector with a direction and length, the unit vector along that direction has a length of 1. This has a length, say v. So, if I take this unit vector and multiply it by the length v, I get the vector itself. So, since I multiply it by the length and I have the direction, this is nothing but the vector itself. Now, this is a working equation and we will use it quite a bit. At the end of last class, I was talking about how you go from a sum of n charges to an integral. what I was saying was that if you have a cloud of charges, many charges inside your cloud, n very large, then what you could do is you could make a box inside this volume. The box could be large or the box could be small, but you keep the center of the box fixed. Now, for any size of box, you count the amount of charge inside the box. So you can plot, or you can make a table. Supposing the size of the box was delta, and you tabulate charge of the box. So you would have 10 centimeters, 1 centimeter, 1 millimeter, 1 micrometer, 1 nanometer, and so on and so forth. And you figure out how much charge is in the box each time. Now that of course is a varying quantity, but you can also find out how much average charge there is, which is you divide by delta cubed. And when you do this for a very large box whose size is becoming comparable to the volume, what you will find is if there are more charges here, fewer charges here, the average value won't reflect the average at the center of the box. So what you will find if you plot this, if you plot q over delta cubed versus delta, you will find some trend. This reflects the fact that when your box is too large, it's not really measuring local properties, it's measuring the entire volume. But after a point, as delta becomes small, it will level off. It will level off till you start getting noise. You get noise when the number of charges in your box are very small. When we do any kind of measurement, whether it is electrostatics or its mass or it's anything, when we want to talk about average quantities, we want to take a box which is small enough that is measuring local properties, which is large enough so it doesn't see the statistical noise. It is possible in most problems to choose such a box, especially in electromagnetics, because the building block of charge is the electron, which has a charge of minus 1.6 into 10 to the minus 19 coulombs. This is such a small number that when you take any practical problem, you have a huge number of charges inside your volume. So you can take a very, very small box and even then have a large number of charges. So you never reach this statistically noisy part of your measurement. But if you were doing some work in VLSI, if you were trying to measure capacitance of a VLSI chip, then you may run into trouble, because you may have only 40 electrons in your entire capacitor, and you are trying to measure the amount of charge that the capacitor holds on average. It will become noisy. Now if we work in this region where the numbers are flat, reliable, we can tile this volume with boxes. And we can fill the entire volume with boxes. Having done that, we can convert our sum. Let us see how we do that. Is equal to 1 over 4 pi epsilon 0 sum on I equals 1 to n. Well, I am now going to change from sum on I equals 1 to n to sum on j equals 1 to m, where these are boxes. And then I say all the charges inside a box are really close to each other. So, all the various vectors r minus rho I are all the same vector, and because of that I will collect all the charge, call it qj, and do r minus rho j, where rho j is now the center of the box, cubed times r minus rho j. It looks like the same equation, but it isn't. There is an important change that has happened. Once I have done this, I am now summing over boxes, and if you remember, the definition of integral is nothing more than summing over boxes. Let me repeat what I just said. I have in one case sum I equals 1 to n qi over r minus rho I cubed r minus rho I. In the other case, I have sum j equals 1 to m qj, maybe I should give it a different symbol, r minus rho j, again a different symbol, they look exactly the same, but in one case I am counting particles. Particle 1 in my cloud, q1 may be here, q2 may be here, q3 may be here. So, when I sum them up, I am not summing up particles that are nearby each other first and then particles that are far away. When I look at the second case, what I have done is I have taken all the particles in this region, summed them up separately and got q tilde 1. I have summed up all the particles in this region and got q tilde 2. I have summed up all the particles here and got q tilde 3. Once I have done this, then I know that as I make these boxes smaller and smaller, as I let delta go to 0, of course, you have to realize I can only let delta go to 0 in this sense. If I let delta go to 0 into this region, it is not correct. So, what we allow in mathematics, we say let delta go all the way to 0, cannot ever happen in physics. In physics, we always have to keep in our minds delta going to 0 means delta goes to a small number, not delta goes to infinitesimally small. So, we let delta go to 0, which means small, and this summation becomes an integral. So, I get the electric field at a point r becomes equal to 1 over 4 pi epsilon naught integral over a volume, the denominator now becomes r minus rho magnitude cubed, the numerator has r minus rho vector, but this quantity qj or this quantity qj tilde, it has to be broken up. This qj tilde is charge in box with sides delta cubed, with sides delta. So, what does that mean? I can write this qj as qj tilde divided by delta cubed into delta cubed. And as you remember from the previous screen, it is q over delta cubed that becomes very flat. And this q over delta cubed, which is the average charge per unit volume, is called charge density. It's got a symbol. The symbol is rho of, well, I have used rho already, haven't I? So I'm going to do a course correction, call this r prime, rho of r prime and dV. Delta cubed is nothing but volume. So I have two kinds of equations. Let me write the other summation right next to it. E of r equals 1 over 4 pi epsilon 0 summation I equals 1 to capital N q sub I over mod r minus rho I cubed times r minus rho I. We have a summation form and we have an integral form. And it is important to understand that these two things are saying different things actually. In fact, there are certain conditions in which they are saying very different things. If you calculate the energy from the integral and the energy from the sum, you will get different answers. So you have to know what you are doing when you jump back and forth from the sum and from the integral. But for most interesting applications of electricity and magnetism, it is this formula that is useful. And for most of this course, we will be using the integral. It's an extremely important set of steps we have gone through. We started with a sum. The sum went over particles that could be anywhere inside the cloud. Nobody said that when you index particles, they have to be close to each other. But then I collected them and grouped them. I said find all the particles that are inside this box, group them together, inside this box, group them together, etc. And then I took the total charge qj tilde, and then I said they are all so close to each other, they are more or less at the same point. So I defined a common r minus r rho j tilde, and I converted my sum to a new kind of sum. It was a sum over boxes, and this sum over boxes goes naturally into a Riemann integral. And in this Riemann integral, this qj tilde is really charge within the box of side delta, which can be written as the charge within the box divided by delta cubed multiplied by delta cubed. This is nothing but average charge into volume of box, which is what is written here. Average charge is usually given this symbol rho of coordinate, and volume of the box becomes dV. Now, in order to fix this in your mind, I am going to do a few problems. The first problem I will take up is that of a line charge. This is given in your book. He uses a slightly different derivation, but essentially the same derivation. You have a line charge. The charge per unit length is lambda coulombs per meter. So if I take a distance 1 meter along this line charge, the amount of charge in that part of the line charge is lambda coulombs. My coordinate system is like this. that is x, y, z. I have put the line charge along the z axis. And then at some point distance r from the line charge, I want to find the electric field. So, what do? There are many different ways of doing it, but let me take a simplifying way of doing it so that you can see the symmetry of the problem. I will take a little piece whose length is dz, which means the amount of charge in there is lambda dz coulombs, and this piece is a distance z above the xy plane. I take another piece which is also dz in size, so its charge is also lambda dz, except it is lying a distance z below the xy plane. Now, if I look at what kind of field these two parts of the line charge cause at this point, well, this point causes an electric field that is pointing slightly down in the xz plane, and this causes a charge that causes a field that is pointing slightly up. Let me rotate the problem so you can see it properly. So, this is x, this is z, this is dz, this is also dz. So, at this point the distance from this piece of charge to where we are, this distance is nothing but square root of this height squared z squared plus the radius squared. The distance from here to the bottom one is also the same thing. So, if you look at the formula for electric field, the electric field depends on the charge, it depends on the distance, and it depends on the direction. So, the electric field has a different direction for each of these, but it has the same magnitude. The magnitude of the electric field is nothing but lambda dz divided by z squared plus r squared. So, these are two equally long vectors, one points up, one points down. If we complete this vector addition, what we end up with is a vector that points exactly sideways. The reason is this angle theta is the same as this angle theta. So, it is a parallelogram and the resultant is a horizontal vector. How much is the length of that horizontal vector? Well, the length of each of these was equal to lambda dz over z squared plus r squared. This angle is also theta, so you have to multiply by cos theta, because cos theta is the horizontal component of these vectors. But there are two of them, so twice lambda dz, z squared plus r squared cos theta. So, my total electric field is going to be along the x direction, is going to be integral from 0 to infinity lambda dz over 4 pi epsilon 0 cos theta over z squared, sorry, twice cos theta over z squared plus x squared. This r squared becomes x squared because we are in the x coordinate. We still haven't fixed what cos theta is, but we can, because cos theta is nothing but the base on the hypotenuse. So, cos theta is equal to this length x divided by square root of z squared plus x squared. So, if I write that out, I get the electric field. The electric field is along x. So, I will just write it as a scalar Ex is equal to, I will pull out all the common constants, 2 lambda over 4 pi epsilon naught times integral 0 to infinity, there is a x that comes out also, dz over z squared plus x squared 3/2. What I have done is I have taken cos theta x over square root of z squared plus x squared and put it in here. The x is not integrated over, so it came out. The square root of z squared plus x squared combined with what was already there to give me z squared plus x squared to the power of 3/2. This is a very standard form. Anytime you see an integral that involves something like z squared plus x squared to the power of anything, you are immediately indicated that you should use a transformation that goes like x tan theta or x tan phi. Theta is already used up. Then dz becomes x secant squared phi, and the denominator z squared plus x squared to the power of 3/2 is equal to x squared tan squared phi plus x squared to the power of 3/2. I have substituted for z, which is x cubed to the power of 1 plus tan squared phi to the power of 3/2. But tan squared phi plus 1 is nothing but secant squared phi. So, it becomes x cubed secant cubed phi. So, I get terms involving x which just come out, and I get terms involving secant squared, I mean secant. So, what happens to my electric field? The electric field becomes twice lambda x divided by 4 pi epsilon naught. I get from dz I get one more x divided by x cubed, x over x cubed, and then I get an integral d phi secant squared phi divided by secant cubed phi, 1 over secant phi. The integral goes from 0 to pi by 2, because when z is 0, tan phi is 0, phi is 0. When z is infinity, tan phi is infinity, phi is pi by 2. This is easily solved because 1 over secant phi is nothing but cos phi. An integral of cos phi is sin phi. So, this whole integral becomes 1. Let me make sure I have got the right answer. So, what you get at the end of it all is that the electric field is along the x direction. You get an x squared divided by x cubed. So, lambda divided by 2 pi epsilon naught 1 over x. Or if you allowed the direction to change, it would be the electric field is in the radial direction lambda over 2 pi epsilon naught 1 over r. So, if you have a line charge and you go a distance r from that line charge, the electric field falls off as 1 over r. Now, 1 over r falls off much more slowly than 1 over r squared. So, it is important that this is understood. What is happening is that as we go further away, we are seeing more and more portions of the line charge. We go out there, we start seeing this part. So, this is not the charge due to a point source, this is a charge due to a distributed source. Very close to the line charge, only this part of the line charge causes the electric field. These parts hardly do anything. Their electric fields are almost vertical and cancelling. As we go far away, now it is mainly these electric fields that do the job. As we go further and further away parts of the line charge contribute. So, that is why it does not fall off as fast as 1 over r square, it falls off as 1 over r. Your book has done the case of a plane, and he just uses the same formula and integrates it. One can do it in a more interesting way. Supposing you have a plane, and we want to know the electric field at some point above the plane. The plane has sigma coulombs per meter square. Now, let us take a ring centered about the xy location of the charge. So, I will put the origin so that the charge is along the z axis, and I look at a ring. So, you have a ring whose radius is r and the thickness of the ring is dr. The amount of charge in that ring dq is equal to the circumference of the ring 2 pi r times the thickness of the ring dr times, of course, the sigma. Now, all points on this ring are equally far from this top point, and for every point here there is a point equal and opposite such that the electric fields are in opposite directions. So, only the vertical component survives. It is exactly the same idea I used for the line charge. If I take opposite parts of the circle, the xy directions of the vectors are exactly opposite, so they cancel out, but the vertical parts add. So, what you get is dE is along z, it is equal to this charge 2 pi r sigma dr divided by 4 pi epsilon naught times 1 over this distance times again you take this angle theta, that angle is the same as this times twice cos theta. Cos theta is nothing but z over the hypotenuse. So, we can replace cos theta by z over square root of z square plus r square. So, the total electric field becomes 2 pi sigma divided by 4 pi epsilon naught. The r dr will go inside. This factor of 2z will come out. So, integral zero to infinity times r dr divided by z squared plus r squared to the 3 halves. Is that okay? I may have made a factor of 2 error here, we will check. So, how did I reach here? For any point here, all points on a circle are equally far from this point. So, I take points that are opposite, I add up the vectors, those vectors cancel sideways, they add vertically. So, you get a vertical vector. Vertical vector means along z. How much is that vector? Well, it is equal to the circumference times the thickness times the charge, that is q, divided by your normalization constant 4 pi epsilon, divided by the distance z squared plus r squared, times your cos theta, because this distance only gives you this part. The cos theta is z over z squared plus r squared. So, the factor of 2 may not be there, we will find out. This is a very easy integral to do. Just take z squared plus r squared as u. Then du is nothing but 2r dr. And since du is equal to 2r dr, the numerator is nothing but du. So, you get 2 pi sigma over 4 pi epsilon naught z times integral du over u to the power of 3 halves. The limits are, upper limit is infinity, lower limit is z squared, because when r is 0, z squared plus r squared is z squared. When r is infinity, it becomes infinity. Solving that, you get the answer, and I will just write it down. You get Ez is equal to 2 pi sigma z over 4 pi epsilon naught. U to the 3 halves becomes u to the minus half over minus half, evaluated from z squared to infinity. 1 over square root of u at infinity goes to 0. So, you are left only with this piece. And so, you get 2 pi sigma over 4 pi epsilon naught times a further factor of 2 times z over z, which cancels out. The electric field is constant, and it is a very strange result. We start with Poisson's equation, we have a charge you go further away, it falls away as 1 over r squared. You have a line, you go further away, it falls off as 1 over r. You go away from a plane and it does not fall away at all. The one kind of reason is given in your textbook, you can read it. Other kind of reason is the further away you go, if you look at the problem in your mind, it looks identical. There is as much of the plane available to you no matter how far away you go. So, the answer can never change. I will continue next time when I will introduce the potential and Gauss's law.